Thank you very much, Dr. Fande, for the introduction to ECS. My name is Asafau Gabramatin. I am one of the co-PIs in CySER, and I would like to say welcome to everyone. We are very excited that you're here for the next 2 weeks, and you probably have seen the agenda for what is coming up in these 2 weeks, and we have tightly packed days with very exciting talks and presentations and some hands-on tutorials. And Pullman has been generous in welcoming you with the good weather. Those of you are coming from outside, so I want to especially welcome you. The next speaker I have the pleasure of introducing is Nathan Kipp. He is the engineering manager at SEL, Schweitzer Engineering Laboratory. He heads the Secure Solutions division there, and he is not a newcomer to CySER, to our program. He has participated in one of our early workshops in the beginning, and I am excited to hear the industry perspective he has to offer, and this will be a nice way to get us introduced to some of the technical things that will happen in CySER. He will be talking about industrial control systems and cybersecurity related things there. Just as a brief background, Nathan holds an MBA degree, but he has also several certificates. He is a certified information systems security professional. He's also a certified security practitioner. So you're hearing from an expert and on things that are relevant in industry today. And I am pleased to introduce him, and he will be joining from where he is via Zoom. I hope, Nathan, you have control of the screen, and I will give the time to you. Thank you.
Thank you for that introduction. And no, I do not have control of the screen yet. If someone could hand me that control, I would be happy to share my presentation. There we go. All right, can everybody see my screen? All right, so thank you for those introductions. I also want to mention that my computer engineering and MBA degrees both came from WSU. I am a WSU grad and very happy to have gone there, and I'm excited to see where the programs have gone since I graduated in 2004 and 2007, respectively. As mentioned, I am an engineering manager at SEL. I've been at SEL since I graduated WSU in 2007. I started at WSU in January of 2008 as a applications engineer supporting our line of security products, which at the time included one device, and it has expanded substantially since then. I've worked as an application engineer supporting our existing products. I've worked as a product engineer developing new products or speccing or designing new products. And I'm now working as an engineering manager in charge of our security product line. So I'm here today to talk about cybersecurity and industrial control systems. I ran through this presentation last night and found out that I was going way too long. So there will be a few slides that I very quickly skip over, just so you're aware. I do feel those are a little bit less important. Our learning objectives today, we're going to learn the basics about industrial control systems. Industrial control, well, with any security program, I feel it's very important to understand the system you're trying to protect and the goals of that system. Otherwise, it's very easy to create challenges for the operators or users of that system that impact their day-to-day operations. We also want to make sure we align security goals with business goals. It doesn't make sense to put $100,000 of security into a business that has $250,000 of revenue in a year, for example, right? We want to make sure we support that business, we allow that business to succeed without creating an overly due burden with cybersecurity. We're going to introduce the driving factors for cybersecurity and energy systems and discuss a little bit about the current solutions and trends we see in the industry. And while I'm keeping this kind of general to industrial control systems as far as a security conversation goes, I am going to be talking specifically a lot about energy systems because that is SEL's bread and butter. We are an energy system provider. So whenever we talk about industrial control systems or really security or risk management in general, it's really handy to build a model to make sure that you're talking about all the correct topics. This particular model was developed by the Department of Energy back in about 2006, 2007. And there's several steps we go through, and I reuse this model because it's effective, but it's not perfect. There are some things that can be improved upon this model. For example, this model suggests that we go through the steps: set security goals, identify assets, assess risks, prioritize, implement protective programs, measure effectiveness, and then create a feedback loop into the previous steps. Well, in reality, we need to be aware that feedback is much more real time and much more flexible in actual practice. For example, we might prioritize and set a priority of things we want to address in the security stance of our system. Then we begin implementing the protective program that we had prioritized and designed, and then realize, wait a sec, the technology is not mature enough for this, or some of our assumptions were wrong, in which case you may need to go back and reprioritize before you actually measure effectiveness. As we go through these steps, we also need to recognize there are three vectors we generally talk about. First is physical security, second is cybersecurity, and then the third is human security. It does not make sense to put a tremendous amount of effort into cybersecurity when a physical breach would cause just as much, if not more, damage. So we need to address all of the risks of all of these three types of vectors, whether it's a physical attack, a cyber attack, or an insider human or malicious human attack. So to go through this, first thing is set security goals. We want to make sure we align our security goals with the business goals of the system or the organization or the business. Here's a quote that I recently found. Our goal as defenders is to reduce the probability of a successful attack campaign that is material to the business, organization, or system. Keyword here being material. A material issue has a major impact on the financial, economic, reputational, and legal aspects of an organization. Now, this is going to be drastically different for each organization. Keeping in mind, we need to know the goals of that organization. Is it a financial firm? If so, we probably want to make sure that we are focusing on maintaining the finances of those customers, making sure bank accounts don't get breached, for example. Whereas if we might be an energy system, we want to make sure that we keep the electricity on. We want to keep the lights available when somebody turns the light switch on. So what we are focused on securing will differ depending upon the organization that we're trying to protect. Next, we want to identify assets, systems, networks, and functions. So here we're going to go into a little bit about what industrial control systems are. I don't want to assume that you guys know this. Industrial control systems are all around us, and you may not realize how prevalent control systems are. Typically, when we start talking about industrial control systems, people think about gas and oil refineries, chemical plants, paper mills. Those large facilities that have a lot of operations that go on inside of them. And that's generally what an industrial control system is at a large scale. However, control systems don't have to be to large scale. They're the same technologies that operate these large facilities that operate, for example, something like a coffee pot or your dishwasher. Planes, trains, and automobiles also have control systems in them. For example, the cruise control feature in your car is a control system. A very simple control system that we are all probably familiar with is something like a thermostat. A control system, at its core, what it does is it reads input from the physical world, performs some logic on that input to make sure things are operating nominally, and then if they ever get out of bounds, trigger an output into that physical world, right? It's the feedback loop. We read something, we don't like it, we make a change to cause that reading to get into a state we like. So with a thermostat, if your temperature goes too high, the thermostat will recognize, okay, we are above the threshold we set of 74 degrees F, so we're going to trigger the AC system to bring it back down below 74 degrees F. This is a feedback loop. In any control system, even in the industrial world, this is the core of it. This is what it's doing. It's reading the physical world, making sure it's the physical world is within bounds, and then causing a change if it goes out of bounds. To get more into the electric sector, into the power grid, everyone has probably seen one of these, or at least most people have, is the circuit breaker that's in your house. This is monitoring the electric usage of your house from a safety perspective. If things are in a safe state, there is not too much current going through the wires, the system will continue operating as it should, and you will have power to your lights. However, if there's a short circuit, if you plug something in that is damaged, or if you have just too much current going through, right? You turn on your vacuum while your dryer and your dishwasher are both going on the same circuit, you will cause a trip because too much current is going through. There's two reasons for this. The first is human safety, right? We want to make sure that we are not creating a state in the electric system that's going to endanger a human life. Second is protection of the system itself. Current going through wires causes wires to heat up and potentially melt, or eventually leading to a fire if there's too much heat that gets generated. So protection of the system itself is the other core feature of things like the circuit breaker panels. And this is a simple example of grid protection that we are all familiar with in our houses. To move this to the actual electric grid, these circuit breakers that we see in our houses get broken out into two components. One is a relay, and here we have the SEL 421, which is one of the relays that we produce, tied to this little square box labeled control, and that's a circuit breaker. This relay is then attached to a line on the power grid that reads the voltage off of that line and current off of that line and make sure things are in a nominal state. If there is a fault, this relay can recognize that and take corrective action to make sure that fault does not cause either a safety issue to people or cause damage to the power grid itself. And so it issues a control to that breaker to turn off power to that line. These relays have grown substantially in capabilities over the years, and we'll get into that in just a second. But again, this is a life safety issue, and so relays are expected to perform at a very high, very fast level to ensure that we're doing everything we can to preserve the health of anybody who might be near a fault. So what's a fault? A short circuit. We have a phase-to-phase fault that is shown here. This is a huge release of energy. And while this is up on a line that's probably away from people, this can occur near people. And if a person is near an arc like this, it is life-threatening. This is why we have such a high severity on the performance and reliability and quality of relays that exist on the power grid. So over the years, relays have had a lot of evolution. To get a little bit into the history of our industry, 1902, Westinghouse produced the first inductive type relay, electromechanical relay. And this is a relay that operates based on induction. So it senses through magnetic fields what is happening on the grid and has wires or plates twist to lose contact to shut off the current that would be going through it. These worked, but they were not super effective. These were not so much for life safety as they were for protection of the system itself, because they did not operate very fast. Electromechanical relays had a lot of improvements over the years up until about 1983, although they are still produced. In 1984, SCL invented the new industry of microprocessor-based relays with our SCL 21, which was produced and first sold in 1984. At this point, we got off of induction and electromechanical and started using analogs from CTs and PTs to measure what is happening on the grid using oscillography, using current flows, using voltage levels to do actual logic and make a better decision on what is happening on the grid and how to protect it. This started to require communications. So at this point is when cybersecurity started to become a concern for the grid, although most people didn't know it yet at the time. The communications in the SCL 21 were pretty minimal. It had two parallel ports on it to allow somebody to plug into it to get oscillography data out. And one of the biggest features in here that enabled microprocessor relays to take hold and grow over time is that we had the ability to start detecting where on a line a fault occurred. So think a transmission line might be 250 miles long. A fault occurs on it somewhere. With an electromechanical relay, you've got to inspect every inch of that 250-mile line to know where that fault occurred. With something like a microprocessor-based relay, we can based upon the harmonics and everything that we see in the echoes on the line, we can make a determination that that fault occurred somewhere between 50 and 70 miles away. So we can narrow down drastically the portion of the line that needs to be inspected before we can bring it back online. And that brings us to today. Last year, we produced the SEL T400L. This is one of the most advanced relays on the market today, and it has a lot of communications capability in it. There is a lot of code in it. This is what we are now trying to start to protect with cybersecurity practices today, because this is remotely accessible. It has a substantial attack surface when compared to previous relays. And there's a lot of things that an attacker can do to manipulate it, to damage the grid, to hurt people. And that's what we as cybersecurity professionals in infrastructure in the US need to support. If we look at the power grid from an operator's perspective, if you go into a control room at any utility, you'll see something like this, where they have a wall full of lines and nodes that are green or red or whatever. So they have a complete view of every single relay on the system, transmission, transformer, breaker, to know if it's in a good state or a bad state, to know if it's on or off. This is enabled through substantial levels of communications. This is why security is starting to become a concern, because now those devices are beginning to be accessible, feasibly accessible by attackers. When we start talking security for the grid, there's really two families of technologies that get brought up a lot: IT, information technology, and OT, operations technology. And there is a little bit of a dichotomy here. In information technology, this is what most people are familiar with. And without understanding operations technology or industrial control systems, there's often a lot of misassumptions about what operations technology looks like. In information technology, it usually sits in a relatively highly dynamic environment. IT groups perform a lot of changes on a day-to-day basis. That's the focus of their job, is change control, change management. We have new employees that come into organizations. We need to spin them up, add them to groups, enable their computers, get them on the network, set up their email, all that type of stuff. They leave the organization, we do the opposite. Information technology usually has a tech lifespan of 3 to 5 years. The expectation for most laptops is they will last 3 years. Expectation for most cell phones is they will last 3 years and then need to be replaced. For communications, IT is generally a best attempt methodology. They try to attempt to send a message, for example. If we look at something like the SMTP standard, Simple Mail Transfer Protocol, it currently says that you shall attempt to retry to send failed emails for up to 7 days, right? That's 1 week on the current standard. Generally, that's not what happens in practice, but the expectation, according to the standard, is still attempt for up to a week. IT is very data-driven, and IT technology generally exists in very controlled environments. If we go to a server farm, a data center, they're generally well-controlled environments with regards to temperature and humidity and the power cleanliness that goes into them. These devices are very high performance, but they are not expected to exist in environments that are not controlled. If we look at operations technology, on the other hand, instead of being dynamic, they're very static environments. You put together an industrial control system, say a substation, and expect it to sit there unchanged for 10, 20, 30, even 60 years in some cases. We don't perform changes on operating systems in the industrial control system environment unless there is a problem that we recognize. If there's no recognized problem, it sits as is for up to 60 years. In operations technology, we are very intolerant of failures, whether that's with devices or with communications. If a device fails, if a relay fails, then that could mean we lose a life, right? If this is a relay that is performing a critical life safety function, such as arc flash detection, and it does not operate when it should, and we have an arc that a human is near, then that human very well could die. Hopefully they just end up in the hospital, but with this technology operating, generally they can walk away from those conditions. That goes for communications as well. There's a lot of relays that operate in multi-relay schemes that will function if that communication dies, but they will not function in as optimal a manner. Rather than being data-driven, operations is usually machine-driven. Most of the communications is machine to machine for automation and coordination capabilities between those different components in the system. And then operations is also very uncontrolled environments. Protective relays need to operate in Antarctica at minus 40 degrees C. Our relays need to operate in the Saudi Arabian desert at plus 60 degrees C. We need these devices to operate in all types of conditions, whether that's cold, warm, dry, wet, high radiation, low radiation. They need to operate all the time. So that is the focus of operations technology. Because of these differences, being static environment, being uncontrolled environments, being generally non-connected, historical reasons, operations technology does not have the same level of cybersecurity history as the IT world. Now that we know a little bit about industrial control systems in the power grid, we need to start assessing risks. In the industrial control system world, specifically critical infrastructure, there's generally 4 levels of threats that we talk about. Level threat 0 is accidents. So we understand accidents can happen. These are not malicious in nature, but they can cause significant damage. And this is something that is taken care of in part by the operations side, but it also needs to be something that the security side is aware of and addresses as well. Threat level 1 is your garden variety, so your script kiddies. Threat level 2 is mercenary. So this is somebody that has a lot of resources, a lot of knowledge, a lot of capability, but they may not have the money, right? And if they're paid to do something, they can generally do it, but it's going to be as they're contracted to do so. And then threat level 3, the nation state. These are enemy nation states. Think Russia, North Korea. Generally, they have a lot of resources, but generally they don't want to attack, right? We're in a unique situation now where with the war going on in Europe, where the likelihood of a nation state event is much higher than it has been in the past. But in general, nation states don't want to attack industrial control systems because that would lead to geopolitical instability and potentially even war, which is something that most nations do not want to deal with. However, in times like now with that war in the Middle East, with war in Eastern Europe, the likelihood of that nation state threat does go up substantially. We have a varied threat landscape that we talk about a lot in industrial control systems as well. So going from left to right here, we have increasing ICS vulnerability landscape. There's more and more code that's going to industrial control system devices. There's more and more shared code. There's more and more libraries that get developed by third parties that get integrated into the end devices. And that means that there's more potential vulnerabilities in these devices that used to be incredibly simple. So if we look back to that SCL 21, it had one communications protocol in it, something that SCL developed called CySER. If we look at that SCL T400L, I don't even know how many communications protocols it has in it. It's got CySER, it's got X.509, it's got TLS, it's got something called T-Series, it's got mirrored bits, it's got synchrophasers, C3718, has Modbus and DMP, has Goose, MMS. There's a lot of communications protocols in there just to show how much that the complexity of these devices have increased and the vulnerabilities that could exist in them. There's a lot more connections to untrusted networks. And this is getting better a little bit as more awareness grows in the industry. But we still see SCL relays connected directly to the internet, where they are directly accessible by attackers. Now, we don't know why. We don't necessarily know if these are touch to production systems or if this is just for somebody to play with, or if it's in the lab and they want remote access from home. We don't know why a lot of these connections exist, but we know they do exist. In addition to that, there's also a lot more connections that are intentionally created for better business capabilities. Now, this may not necessarily be correct from a cybersecurity standpoint, but there is a business need for it, and so it does occur. There's more humans that touch these systems, and generally they are less trained than they used to be, so that's an increasing threat. Supply chains are getting more complicated. Back in 1984, there wasn't a whole lot we needed to deal with regards to supply chain. I mean, the code was all developed in-house. Most of the parts were produced in the United States. But now we have parts developed in China or produced in China, in Taiwan, in India, in Singapore. And all of these get fed into the relays that we produce now because we don't have fabs just in the United States anymore. And it's not just that they're being produced internationally, it's that they're going through shipping, they're going through customs. There's a lot of potential points where these devices or code can be tampered with. This also means the end device integrator does not necessarily have full knowledge of those components. And so there's a lot more trust that is given around when we start building these more complex devices. In general, there's a lack of detection capabilities in industrial control system devices as well. This is not the IT world. Most of the monitoring capabilities are focused on operations and not so much on human behavior or human triggered incidents. So that's something the industry is struggling with and improving upon. And then there's also an increase in demonstrated attacks over the years, and I'll get more to those demonstrated attacks in a minute. To just show you the potential of an attack on an industrial control system, this is a picture of a generator room at Sayano-Shushenskaya Dam in Russia. This is a very large facility. There's 10 650 megawatt generators here. Each of these generators weighs 1,000 tons or 2 million pounds. And we're just looking at the very top of the generators here. So each of these nubs you see in the middle of each of these circle is the top of the shaft of each of these generators. Now, there is an incident, an accident. This was not maliciously caused. This was not considered a cyber attack, but there was an incident at this dam. One of these generators was offline for repairs. As moving equipment does, it had some fatigue stress in the shaft, which caused it to start getting imbalanced. So they took one of these generators offline for maintenance, and when they take it offline, they lock it into place. So it can't turn, it can't spin. It's in part for human safety. When it does that, there's not supposed to be anything that goes through this, whether it's electricity or water or anything else. What happened was an operator accidentally opened the control gate to the penstock to this generator that was offline. And water comes flooding in through this huge lake behind this dam, hits the generator, which is locked in place, and there's no way for this water to go. So it pushes up. And it pushed this 2 million pound generator straight up, shot all the way up, hit the ceiling, exploded when it hit the ceiling, caused massive damage, massive flooding. This is the aftermath. 75 people died. It's estimated that this cost Russia $1.8 billion in about 10 years to recover from, not to mention the loss in power to a lot of people and businesses, which caused a larger economic hardship. But even though this was an accident, this was a remotely controlled control gate that if an attacker had gotten into the system, that if they wanted to cause this type of damage, they could have. Some specific examples of attacks on ICS systems. There's 4 that I have here. Maroochy Shire is a shire in Australia. This is kind of an insider attack, but also shows some of the importance around having good security policy and adhering to that policy. Maroochy Shire had a contractor that they had on the system that they terminated. They had some issues with him. They fired with him, but they did not revoke his access credentials. And so days after he got terminated, he logged into the system remotely and opened all of these sewage gates around the city and dumped raw sewage all around the city, creating huge mess, huge economic hardship, and not to mention health issues for the entire city. It was found pretty quickly, but this is an example of not having or following good processes. We have Stuxnet. Stuxnet came out in, I want to say 2011, although I don't remember for sure. This is an example of the first piece of malware to have a physical effect in the physical world. Stuxnet is malware that was obtained and put into the Natanz nuclear plant in Iran. And what it did was it caused centrifuges to spin out of balance, to spin too fast. But meanwhile, it presented to the system operators that everything was working normally. If you look back to that operator board that I showed a few slides ago, the operators were looking at that and everything looked like it was good. However, the generators were spinning out of control, and this caused physical damage to those centrifuges, putting Iran's nuclear ambitions back by years. Metcalfe was an incident outside of San Francisco. There's a substation referred to as Metcalfe outside of San Francisco where that was attacked. And we don't necessarily know why. We don't necessarily know by who. But what happened was they cut communications lines and they shot transformers and caused a transformer fire similar to what you're seeing here on this slide. We don't know who or why. There's suspicion that it might have been the US testing our own infrastructure because honestly, it caused minimal damage to the grid as a whole. So somebody who wanted to test our own responses to an incident like this, it's actually a relatively good site to do so. So this could have been done by a US entity, or it's possible that it was done by an international entity attempting to test our response as well. But this was a combination cyber physical attack because they cut communications lines, they entered into the system from a cyber perspective, and they also physically shot the transformers. And then the last attack example is probably the most serious out of all these. It actually combines a lot of things that we don't want to see in cyber attacks on industrial control systems. Ukraine, I believe it was December 15th of 2019, Ukraine was the victim of a cyber attack purportedly by Russia, where they got into the system, actually got quite widespread into the system because they attacked an Active Directory server and got into it and managed to extract credentials so they could get throughout the system. And what happened was they managed to log on to a bunch of routers and firewalls, do malicious firmware updates to brick those devices to make them go back to the manufacturer to become usable again. And they got into HMIs, human machine interfaces, and clicked buttons to trip circuit breakers to turn off devices and generally cause grid instability. The good thing that Ukraine did in this situation was they were able to limit exposure pretty well. They were able to go back to a state of manual operations to get power on relatively quickly. However, they did a lot of things wrong. One is have a corporate Active Directory server operating both on the corporate side and on the operations side. They got in through email and used that email to retain access to the computer of the user whose email it was, and then use that to get to the LDAP server. And then scraping the LDAP server, they figured out how to get to and how to get into the operations center. Best practice would dictate you have different Active Directory domains for your corporate side and your operations side. The attackers also did things wrong, though, and that's why Ukraine was able to recover as quickly as they did. They didn't understand the system they were getting into. And you can see on videos that are recorded an attacker manipulating the mouse in a remote desktop session on one of these HMIs. And they obviously don't know the language and they don't know which button is going to do what. And the first HMI they hit, you can see this video, they're kind of clicking around, not knowing what's what. And then they figure out the button that does what they want it to do. And then that gave the defenders time to realize something weird was happening. Right, so they did that first HMI and turned off breakers there. Then they moved to another HMI and much more quickly hit the button they wanted, moved to a third one, much more quickly hit the button they wanted because now they know the pattern. And at this point, Ukraine recognized it was an attack and they were able to contain a lot more effectively. The attackers also shot themselves in the foot a little bit as well because they bricked the routers and firewalls. They actually prevented themselves from expanding their influence on the system. And so they had a little bit of out of order operations there. Instead of turning the system off and then killing comms, they did it simultaneously and limited the damage they could do. So assessing the risks, then we want to prioritize. I don't have a whole lot to say on prioritization because this is very specific to each entity on how they want to prioritize depending on business goals and threats. Generally in the energy world, we want to prioritize on those things that are remotely compromisable, remotely exploitable, and those things that will impact the availability of the electricity itself. Once we've gone through that, then we can actually start doing the fun stuff and implementing protective programs. To implement protective programs, we have this model we refer back to frequently called a Purdue model. And we have it broken up into 7 layers, 8 layers. Down at layer 0, the physical layer, this is where those physical components of the control system sit. And this is where the sensors sit, the CTs, the PTs, the thermometers. And this is where the output sits, the circuit breakers, transformers, furnaces, AC units. One level above that, we have the protection system. This is where meters and relays sit. Generally, communications between the physical world and the protection layer are analog in nature. There's not a whole lot of digital that occurs here, although some of this is becoming digital as certain standards and technologies become more prevalent. Above the protection, more characteristics on the protection level is this is very high performance, very application specific, and very real time oriented, because this is life safety. Milliseconds of operations in this level can mean the difference between life and death for somebody who is near an arc flash. Moving from protection up to automation, there's a lot of the same functions at the automation level. However, it is more of a coordination type level, right? Instead of having real time, we sense a fault and we need to act on that fault. This is more monitoring when loads come onto the system, when we need to influence generation to bring generation up or down. On the grid, load and generation has to be balanced. If it's not balanced, the grid will go unstable. And a big goal of this automation portion of the system is to maintain that balance as the grid is slowly changing states. So it does still have some high performance needs there, but we're not talking milliseconds. We're talking seconds as kind of being the scale of expectation here. Moving up one level is the access level. It's access control. Think firewalls. Think encryption devices. Moving up one level, we've got level 4, or which is referred to as the SCADA or DMZ. And you'll note on the left side, I have an H2M versus M2M between levels 3 and 4. Generally, level 3 and down is almost entirely machine-to-machine communications. Level 4 and up is where humans interact with the system. And so that's one of those delimiters that we can easily state that, hey, certain activities occur here and other activities occur here, breaking it into zones of trust, if you will. SCADA is where the operators access the system and interact with it, where that board in the operations room comes from. SCADA stands for System Control and Data Acquisition. And then DMZ, standing for Demilitarized Zone. We can also think of this as a buffer. So any data that's in layers 1, 2, and 3 that needs to get exported out would get exported to databases in the DMZ, historians, backups, et cetera, for humans to interact with or use as needed in the future. Then we have a perimeter before we finally go to corporate. And perimeter is also an access control zone, also firewall based, but different set of rules. And then corporate is people like finances, and they're part of the system because metering data needs to get used by the finance department to determine revenue for the company. So even that level 1 data is necessary to have in the modern world in that corporate environment. And then we have layer 7 on the side, labeling it people. Even though humans generally interact with the system at layer 4 and above, we do need to recognize that humans interact with the system at all levels. These devices, these systems need to be commissioned. They need to be maintained over time. If a CT or PT fails, it needs to be replaced. If a relay fails, it needs to be replaced. So humans are part of the system. There's a lot of communications in the industrial control system world. If something has done communications at all for anything in the last 30, 40 years, it is in industrial control systems, specifically electric systems. We deal with serial communications regularly, EIA 232 or point-to-point serial communications. We also deal with 422 and 45, which is 2-wire, 4-wire, multi-drop serial communications. We deal with frame relay. We deal with plain old telephone system dial-up communications, although that is going away as the telephone systems abandon their lines. We deal with leased lines. SONET or SDH, synchronous digital hierarchy, Ethernet. We can also go across any medium that has ever existed, whether it's copper, fiber, radio, satellite, cell, all of that is fair game. Something that makes it really challenging to protect communications in our industry is that you can have all of these technologies between any two given points that might want to talk to each other. You can have one of them in newer systems. Generally, it would be Ethernet. You can have a combination such as SONET and Ethernet, or there are some systems that have been slowly grown organically over the years since 1984, and they will have channels of every single one of these between 2 points. Makes it very complicated to be able to protect communications in some systems. There's a lot of defensive strategies we talk about. The big thing that is probably the most important is user training, because users are the attack points to most systems and the biggest vulnerability, whether it's clicking on a link in an email that they shouldn't have, or visiting a website that they shouldn't have, or just not being aware of the system and doing something they shouldn't do. Training is incredibly important to protect industrial control systems. We want to reduce attack surface as much as possible. The trend up until now has been to actually make relays more complicated. And that's due to market pressure, that's due to other competing vendors, that's due to standards bodies, that's due to regulations, but everything's been getting more complicated over the past 40 years. And that means there's going to be more vulnerabilities in systems. And so there's a big effort going underway right now to reduce the complexity of each of these components of the system. System architecture is incredibly important. We need to recognize that industrial control systems are systems. Relays are not general purpose computers. A lot of people have this misperception that they are, and that has led to problems over the years, one of which being the initial critical infrastructure protection regulations that came out in 2008 required all critical cyber assets, including relays, to have anti-malware installed on them. These are not general purpose computing systems. They are very specific application built systems that cannot run anti-malware. And making sure we understand the system and that all of these are part of a cohesive system means that we can put the correct security technologies in the correct places. Redundancy, monitoring, data correlation, automation, cryptography, updates, access control, all of this, for the most part, exists in most industries. But for industrial control systems, training, attack surface reduction, and system architecture are by far the most important defensive strategies we have right now. There's a lot of guidance on cybersecurity for industrial control systems. NIST Special Publication 800 is kind of what drives everything. I mean, this is written by the federal government for the federal government and IT systems. There's a lot of good stuff in there for industrial control systems as well. The NERC standards, the NERC Critical Infrastructure Protection Standards, are based in large part on NIST SB 800. ISA, IEC has a lot of standards as well that all refer back to SB 800 as well. So SB 800 is kind of the guiding document that we all should be aware of. The NERC Critical Infrastructure Protection Standards have become regulation, and they did so in 2008. This is a set of about 14 standards that have requirements such as classifying devices on the system, having chains of authority and sign-off and approvals and reviews for changes to the system, having avenues of communication to convey to the authorities incidents of attacks or sabotage, provides guidance on hardening relays and computers that might exist in the system. There's a lot of information there. The critical infrastructure protection regulations are something that we at SCL tend to refer to as what standards. They tell you what should be addressed, but not necessarily how to do it. ISA IEC is another standards body, and they have a couple of standards that I've been working with a lot recently, 6443 and 6351. These are more how standards. While NERC tells you what should be addressed, ISA and IEC tell you how to address it. They want to make sure you do it in this prescriptive manner. And there's some good to that, and there's also some not so good to that. I mean, the good is that if we want to have a system that has a whole bunch of vendors participating in it, there's going to be some interoperability if they're all following the same IEC, ISA, IEC how standards. However, this also stifles innovation and future security because these standards are looking at what exists today and what exists in the past and making sure that gets put into devices. But it doesn't really look forward and say, hey, we might want to change things in 5 or maybe even 1 year or 5 years or 10 years, putting an additional burden on system operators to continually update and manage those systems. And by the way, it is very difficult to update some of these energy systems. For example, look at a utility such as Southern Company, which crosses 5 states. Right, they are the primary generation transmission facility in Georgia, Alabama, North Carolina. They do a lot of work in Florida, Tennessee, and Southern Company across 5 states has probably, well, there's 3,000 substations that I'm aware of. I know they have more than that because those are only their SIP regulated sites. And each of those substations, they have hundreds of devices, right? And if you have a team of 20 people that has to manage 1,000 sites, each with 200 devices spread across 5 states, it becomes very burdensome to do updates. And so that's one of the drawbacks of really strictly specifying how things are done, because it's really looking backwards. There's a lot of reuse of IT technology and OT systems, and this is one of those things that 62351 dictates is thou shalt use TLS for end-to-end encryption for certain protocols. And this means we have to put TLS into relays. And as we all know, TLS doesn't have the best track record for keeping vulnerabilities out of systems. I mean, one of the first major ones that I had to deal with was Heartbleed. If you have TLS in your system and something like Heartbleed comes out, that means you need to go out per regulation and update all of your devices immediately. And when we're talking thousands of devices that have poor communications to them, and they have other standards, such as the NIC PRC standards, protective relay and communication standards around updates and how devices shall be tested before being placed in service, it's very burdensome. With all the regulations and work that people have to go through, the average cost to do a firmware update on a single relay in the United States right now is $15,000. So if we're talking thousands of relays, it becomes a huge economic burden to do these updates. Some of these technologies are not too bad though, right? So syslog, for example, is actually a really good technology to start integrating into OT systems. But some of these others like TLS and X.509 bring with them a lot of drawbacks that are not really apparent until you've actually have to suffer through dealing with them. We also do a lot of reinventing of IT technologies for industrial control systems. The big one I'm going to talk about here is software-defined networking. Software-defined networking was developed by Facebook and Google for use in their data centers, highly dynamic environments, right? They want to make sure they have centralized view of the network to make the best decision possible for forwarding packets. And they wanted this because if a new cat video gets posted, and all of a sudden you have a whole bunch of people looking at this cat video, you need to spin up a whole bunch of virtual servers and the virtual network to be able to supply this required video to everybody who's requesting it. So they built SDN to be more dynamic. In industrial control systems, we are generally very well engineered systems. We know exactly which relay is supposed to talk to which relay, we know which PLC is supposed to talk to which PLC. Using legacy internet in industrial control systems is problematic because it's not deterministic. It takes time to recover in the case of a failure. And there's also a lot of unused bandwidth, right? If we look at a network loop with something like RSTP in it, we actually block links from being used to prevent network loops and only enable them in the case of a failure. With software-defined networking, instead, what we do is we have a centralized controller have awareness of the entire system, all the switches, all of the links, all of the packets going through. And we can predetermine, we can pre-engineer all of the traffic flows that we want between all of the machine-to-machine communications. So we can say relay A can talk to relay B and C only, but not relay D, and pre-engineer those flows because we know all of the paths between them. We can set primary flows, secondary flows, tertiary flows, quadrilateral flows. We can handle all of those failure conditions much better than legacy networking could. This was developed in part for operational efficiency, but it also has a huge security component because we can dictate on the Ethernet network exactly who can talk where, looking at the incoming port, looking at the MAC address, the IP address, the protocol in use, the service being used. We can dictate exactly what is allowed on the system and what is not. So if an attacker gets in, they are incredibly constrained by what they're allowed to do. If they break in physically and the port they're attached to is not allowing traffic on at all, then they're not going to be able to talk to anything. If it's not allowing traffic for SSH, for example, they're not going to be able to probe any of the terminals of any of the relays. So it does quite a lot for security at this point, and it is probably the best technology for getting towards one of the new trends of zero trust security. Other technologies we have reinvented or repurposed are IPsec, MACsec, and OAuth. IPsec we have simplified a lot. It's a very complicated crypto standard. And generally in industrial control systems, we don't need the complexity because we don't need that level of interoperability or flexibility that it's used for in the IT world. And so we can strip out a lot of the features that are unnecessary for our users. This primarily means you can use good cryptography without complexity, without misconfiguration, and with having good faith that it is doing what it's supposed to be doing. MACsec is another crypto technology we've employed, and OAuth is starting to be used to simplify some of the protocols we have to put into relays. On the previous slide, we had a bunch of IT technologies such as LDAP, Radius, TACAX, and we're getting more and more requests from the industry to employ all of these technologies directly in relays, but that increases the attack surface. Using something like OAuth that can wrap all of these technologies and then offload the LDAP and Radius and TACAX and all the other access control stuff onto another box means we can start reducing the attack surface of the relays and not having as much code in those boxes. We minimize the updates that way, we minimize the potential vulnerabilities, and we actually increase interoperability for all of our different customers who have different technologies in their systems. Finally, the last step is measuring effectiveness. It's really, really difficult to measure effectiveness and security of industrial control systems. Generally, we do something like tabletop exercises. We look at what we think our system state is. We play games and say, hey, what happens in this scenario? How is the system going to react? Do we know how it's going to react? How do the processes fit? How do the people? Do we know who's doing what? Really effective, really low cost exercise to measure the security of your system. Failure and recovery exercises are often used. And this is generally done in coordination with the OT maintenance cycle. So for example, you have a coal plant that has to go offline for cleaning of the boiler. You'll try to align your cybersecurity exercises with that maintenance cycle because this limits the possibility that you will cause an adverse impact to that system while it is live. So it's a great opportunity while it's doing its own maintenance to do your failure and recovery exercises. Penetration testing is something that comes up a lot, and it's actually a really good practice, but make sure you have an analogous system to test against and not your production system. A lot of the effective penetration testers out there don't know industrial control systems, and they don't know the impact that certain actions can have on the grid. We don't want to turn power off to Washington State in a penetration test accidentally. That being said, penetration tests are good, but make sure you're doing it in a lab environment, make sure you're doing it in a simulated environment, make sure you're doing it in a copy of your production system. As a parting message, ICS cybersecurity has some unique considerations when compared to the general security world in information technology. There's a lot of differences. There's a lot of specific needs. We generally think of systems as systems of multiple components that each have their own specific purpose, right? They are not general purpose computers. Application awareness is key. We need to know the performance characteristics of the system and its applications, and if it's a life safety system, if it is a grid protection system, if it is a food production system that can handle going offline for a minute or 5 minutes or a day. Application awareness is key because that helps us determine which security technologies are appropriate as well as how much security to throw at it. It's a challenging environment for cybersecurity. This is not an industry that traditionally has had a lot of cybersecurity expertise, and there's not a lot of experts in there even today, although it is getting better. Back when I started at SCL in 2008, there were probably a dozen people in the entire world that I would have considered as industrial control system cybersecurity experts. That has grown substantially in the last 10 years. But when I started, it was very small and still is. And there's tremendous room for innovation. There's a lot of adopting of information technologies. A lot of that can be adopted as is. A lot of it needs modification. But then there's a lot of room for innovation because industrial control systems do have the operation side, which is very mature. And that operation side can often be reused for security purposes, just with a little thought and a little ingenuity. I want to thank you very much for inviting me. I think the CySER program is amazing. As a WSU grad, as a cybersecurity professional, I'm very excited to see where this will go. I think it's a great opportunity for WSU and the industry in general, both the industrial control system, cybersecurity industry, and the infrastructure and the information technology industry. So thank you very much. Thank you for inviting me. Thank you for listening to my presentation. And at this point, I can open it up for any questions.
Thank you very much, Nathan, for that excellent introduction to this topic. Nathan asked me when we invited him to talk what his audience was, and told him primarily students. They come from different backgrounds, different levels, and then also other people who do research. And I think he did an amazing job addressing both those of us who need introduction and those who might have done a bit of work in this area. And if you have seen your schedule, on Thursday in the afternoon, there will be a field trip to SEL, where Nathan works, and some of the relay protection and other things that they do, you will have an opportunity to visit and look at what they do. We have some time for questions. I would open it if you have any, including the ones that are following us online. I'll start with Professor Schulz. I see your hand up, so go ahead and ask the question.
Yeah, thanks, Nathan. That was amazing and a great talk. And I can see that you're going to get picked to do a lot of other talks to help provide an overview. So I think for this whole workshop, I think it was your slide, your flow chart slide. I think, yeah, that one. I think that is really great for us as we look at the next 2 weeks to look at. I think you did a great job of talking about the complexity of cybersecurity. I think when people think about cybersecurity, they jump in and think about the solutions. And I really think you did a great job of talking about the systems, the background, and the different stages of cybersecurity that, and I think that's so important. And you've talked about that. So thank you so much. I think this figure is probably a crux of so much of what we're going to be talking about the next 2 weeks. I guess my question is, as you see in the next 3 to 5 years, particularly for our students, how do you see cybersecurity of today and the cybersecurity of tomorrow? That if you were a student sitting in their chair right now, what would you suggest they focus on, or what kind of background activities? Obviously, as a power engineer, the OT side is near and dear to my heart, and your activities. But in general, where do you see us moving in the next 3 to 5 years?
That's a great question and very difficult to answer, because if you ask me that this week, I'll provide one answer. You ask me that next month, I'll probably provide a different answer. It is a constantly changing field, right? And really much in the information technology world, it's changing drastically. In the industrial control system world, it's not so fast. In the industrial control system world, we're generally very conservative. We move slowly. We want to make sure we know something works well before it goes into service. We are very resistant to change. And that's one of the biggest struggles that I've had as a cybersecurity professional in this industry, is I want to move quick and the industry doesn't. That is changing a little bit, but we do have to recognize that it's a balancing act between change and being secure versus maintaining the reliability of the system and methods that we know have proven to work. As far as students go and what they can do, this is a one of the big problems we have is getting help in this industry. There's a lot of great cybersecurity professionals out there. A lot of them have a lot of trouble adjusting to the different environment. And one of the biggest asks I have for students who are learning this, or for people who are teaching, is teach open-mindedness, teach flexibility, right? Even though you have something that has worked well in the past, or has the way you've been taught something, it might be for a specific application or a specific scenario, or maybe even general. And we need to be able to take our knowledge base and adapt it to new situations, to new business needs, to new systems, as the technology changes, as the business need changes, as our market changes, as the attacks change, right? And in the electric sector, what's most important is keeping the lights on, period, right? And there's a lot of technology that we can put in there that might keep you more secure, but will not do a better job at keeping the lights on. And that's something that we struggle with, is identifying those technologies or developing them that will actually do both. For example, going back to TLS and X.509, technologies that have been around for a long time. X.509 being the standard for public key infrastructure in the US, actually around the world. And putting PKI into relays or into industrial control systems sometimes works. But more often than not, I have seen operators misuse it. They put it in because they have a shop with 5 people who do the communications and the relaying and the automation and the security and everything else. And they don't have the time to learn how to properly apply this technology or implement it. And they need to by regulation. So they just put it in without understanding it or its ramifications or how to do it properly. And I see X.509 being misused drastically. They share private keys. They put the same private keys on multiple devices. They set key expirations to be 100 years, so they never have to deal with it again, right? All considered bad practices from the X.509 standards. But it's what they do because it's what they have the ability to do, the resources to do, and they don't know better. So understand that it's not an ideal world. In the industrial control system world, you have to have a passion for education. You have to be willing to repeat the same message over and over and over and over again. But more so, you need to make sure you have an open mind and are aware that this is not the traditional world that cybersecurity professionals are trained in.
Great. Thank you so much for that and for really kicking off our 2 weeks with a great intro.
Very welcome.
Thank you, Noel. Thank you, Nathan. Anybody else got a question from the audience here? You must have done an outstanding job. It was clear. I'm going to also mention that SEL is heavily involved in what we do at ECS. Many of them serve directly in the Executive Council at ECS. And for those of you who are in computer science, if you've heard of the lunch and learn on Fridays, Greg, who's a member there, he's the one who's behind it. So we're grateful for SEL, the support and everything that you do. And thanks again, Nathan, for an excellent introduction. Bernie, I'll give it to you to introduce the next speaker.
Very welcome. Thank you.
Thank you, Nathan. This is Bernie Van Wee. I want to thank you as well. I'm the PI on the CySER project. So